All right, good morning. Welcome to this webinar on collaborative model-based systems engineering in support of concurrent design. Happy that you can join us. My name is Sam Hirene. I work for a company called the Rhea Group. With me, I have Ilaria Roma from the European Space Agency, and together we'll give you this presentation or webinar. So it's split in two parts. First, Ilaria will explain concurrent design at the CDF and give you some insights, and then I will take over on how collaborative model-based system engineering supports that. Ilaria, I give the floor to you. Please tell me when I need to go to the next slide.
Yeah, thank you very much, Sam. In fact, you can jump immediately to the first chart. As Sam has mentioned, my name is Ilaria, and I'm the head of the Systems and Concurrent Engineering section at the European Space Agency. And I'm happy to be at this event, which talks about innovation, as we want to bring on the table, let's say, one of the most essential ingredients to innovation. And going to the next slide, Sam, I gave it a talk, and I thought no innovation can take place without people. People getting some creative and new ideas, but also the ideas need some discussion, interaction among people, exchanging thoughts, information, but also technical data, of course. And then driving these discussions and refining discussion until we get to the targeted and useful application. Well, at ESA, at the European Space Agency, we have a place for that to happen. There's a facility which is specialized in connecting and bringing together multidisciplinary teams. So teams having people having different expertise. And they can get together and discuss new concepts applied to space in that case, but not necessarily, and applying a methodology which is called concurrent engineering. So very much connected to this collaboration that you see in the title of this webinar. We can go to the next slide, and in which I gathered these pictures of this facility, which is something that we have for more than 20 years now. And it started like as a prototype, really a very, very temporary room we used to call the barracks. And so the applications and the use cases that in these 20 years we have managed to, let's say, to have, conduct, and show benefit of, brought to a very well-established facility, which now exists, and you can see in the website we have included some links at the end of this presentation. Next slide. But you can tell me, yeah, but what is this CDF? Oh, you can ask me. The CDF is the concurrent design facility, is a so-called integrated design environment. And I'll tell you a little bit what are the elements which makes this environment to be called integrated. And this is available to all the agency, the European Space Agency directorates, so all the groups of people working on the various categories of space missions. But not only, it's available also to external partners, and we are trying to make this more visible to the whole industrial setting overall in Europe. And we started the implementation of the concurrent facility, and its application started in November 1998 on an experimental basis. And initially, the environment was conceived for feasibility assessment of space missions. So basically, you get a new idea for an innovative mission or a new space mission, and you want to understand whether technically and programmatically that is feasible. So are there all the needed technology in place, and is the budget viable to build and to fly such a mission? I talked to you about the main ingredients, and of course, one of the main ingredients, as I mentioned to you, is the team of specialists and the multidisciplinarity of those specialists. But not only, because of course we need creative ideas, we need discussion, but we need some sort of formalism in this discussion. And on top of that, we need tools, data, models in order to share this sort of information in a structured way. And also one of the essential let's say, ingredients that make concurrent engineering and concurrent design possible is the simultaneous participation of all the stakeholders related to the design or to the development of a certain activity. So, including technical and programmatical actors. So, you can imagine in the space mission, so from the hardware, from the building and testing the spacecraft until the costing and the schedule, well, all these actors have to be in the same place at the same time, discussing and making this sharing of information. So this is really what makes collaboration and concurrent design special. If you go to the next slide, I want to share with the audience some pictures of this environment and this facility at action. And you see, in fact, the team at work, and you see the various, let's say, disciplines in these settings. There is even a specific shape of the sitting in the room in order to encourage and to foster the dialogue and the exchange. And the peculiarity of the approach, indeed, that is a multidisciplinary, holistic, so that each system is looked into from the various perspectives, with a systematic process. So we enter the room and we go through the design steps and based on the objectives of the activity in a very structured way, with a centralized, let's say, control, if you like, because there is a team leader leading the team and leading the happenings inside this, the steps which make the design possible, and it's very much focused on the customer expectation. The customer himself is part of the team in order to make sure that whatever product, and in our case the design, is developed, is then in line with what the customer asks for. And this methodology is based on iterations. So each specialist presents this design, discusses with the rest of the team, and baseline it or change it accordingly to the discussions that take place in the room. So every decision there is taken and is made by a consensus, and there is an awareness of all the aspects that comes together to the design. And the next slide shows also that even if the CDF and the concurrent engineering, concurrent design at ESA takes place for space mission in the early phases, so really at the conceptual phase, when we invent, we create a new concept of a mission, we try to let's say, touch base with some sort of reality with some visualization techniques. So that's why you will find as part of the facility models which are related to graphical representation, which are like rapid prototyping or some digital mock-ups. And we are working to inject also augmented reality already in the early design phases to stimulate the innovation and creativity of members. The next slide replies to a question, which is, why do we need concurrent engineering and concurrent design? Because in the past, missions, space missions, would be designed with sequential engineering standard approach. Well, that's absolutely true. However, this was coming along with some communication gaps among the specialists, because they would design missions in isolation in their offices, and then they would come together, get together at official milestones in which some discrepancies would be found among the subsystems, among the various aspects, so requiring extra time, extra resources to be put in place. So basically, the concurrent, the collaboration, and be at the same time, at the same place, or at the same remote place nowadays, would make the process much more efficient. And also in the development, you can make also a parallel in the development phase. also the collaboration and concurrent engineering, of course, reduces the times, and we can parallelize actions that are somehow independent, and therefore we can also reduce the risk of engineering changes that would be required if it would be disconnected and not talking to each other. So concurrent engineering is there to bridge the gap between the designer and the user, and also, if you go to the next slide, some is there because whenever we are dealing with complex system. Space is surely a complex system. There are already many subsystems and interfaces to deal with inside the spacecraft itself, but not only. If you go along the life cycle, we have to design this spacecraft, we have to conceive a way to assemble, test the various items at the subsystem and system level. We have to think about how to launch it in space. We have to think about how to get data and control the spacecraft in space with the ground. We have to think about standard operation, dispatch of data, and we have to think about the end of mission disposal. So now, if you click, there are some arrows telling you that all this life cycle has to be captured already from the early phases, bringing the amount of information, data, and expertise to a very substantial number. So there's a lot of, voices to be listened to, a lot of data to be put together in order to have a coherent design. So if you go to the next slide, we see also that this approach becomes very essential in terms of technology. And I want to, we discussed together with Sam in the preparation of our message. This is something that we want to share with the audience, since today we are talking about innovation and technological innovation. Concurrent design is taking a very important role in innovation and technology and R&D, because when designing space mission, but whatever complex system, we in the team, the enabling technologies or improvements are identified, and this is obviously going to inform the strategic lines of what needs to be developed in the future. So by being together, by putting together a mission and a concept with the creative ideas, we can sketch the lines of the future R&D and technology development. On the contrary, and this is also on the slide after this one, so we call this technology push, but we also have, we call this technology pull, but we also have a technology push. So whenever there is a new technology being developed, we might want to analyze the impact of that technology or of a subset of promising technologies on the complete system. In our case, this is the space system, but it can be, of course, a message that can be extended, because imagine, just to give you an example, if we are working on miniaturization, for example, on several subsystems of a spacecraft, we want to combine this technology, we might want to assess what is the impact at system level on the power, on the configuration, on several other items. So this is an application that we find very important and relevant for this audience. Now, going to the next chart, we want to share with you the fact that, okay, we have applied this collaboration, we have applied this concurrent design, and we believe that we have to be here today and share it with you, because this is bringing a lot of benefits. Of course, every study duration in space and for what we are doing has been, let's say, reduced by factor 4, so we can make studies in much shorter time. And there is also a reduction in cost. Of course, it's not proportional, because all this infrastructure, all this facility needs, of course, to be managed and maintained. However, it's for sure no doubt that the quality of the activities run with the concurrent design has been improved, because we have a coherency, we have a lot of, let's say, side products, which is enabled by being all together in this same environment, discussing around the same topics. And also, an important role that the CDF and concurrent design has gained throughout 20 years at ESA is the fact that we can capitalize the knowledge, because we have databases, repository of information, and also because the report of each of these activities becomes part of the, let's say, invitation to tenders to industry. So basically the CDF is preparing somehow for the technology development taking place in industry across Europe, and not only, because there are also the international partnerships. So we take a place in there. It's the CDF became a sort of a reference point, if you like, in this technology world. And we are approached whenever there is, let's say, a big endeavor or big, let's say, event of preparation of the proposals, also to be presented to our member states. CDF plays an important role because it brings together the perspective of several people inside the agency, and sometimes even from, let's say, external advisors. So there are benefits, there is a process, and in the next slide, if you can scroll it, push it some, these benefits have been quantified over nowadays more than 300 studies. You'll find this poster in the archive of our website. It's we have now increased so much the number of studies that they don't fit anymore in this colorful poster, which I wanted to share with you because I believe it's some, let's say, nice, attractive, but also schematic in the way it is presented. And it brings you the message that concurrent design can be applied to several categories of missions. And here you see they are divided per planet, per program. And but not only, concurrent engineering is a methodology that you can apply to every multidisciplinary and complex system. And if we go to the next slide, I want to stress on the fact that, yes, concurrent engineering is there, but it doesn't come for free, because, as I told you, it's people sharing and talking about creative ideas, but we are talking about technical matters. So exchanging data and information requires models, requires tools, and requires standards, because we have to speak the same language to make sure that when we share the information, we can understand each other and we can be on the same page. And since collaboration requires the involvement of many actors and stakeholders, this is an essential message which Sam will elaborate upon. And before I give it to Sam, just to give you an idea of how many actors in Europe are using already this concurrent design with a sort of concurrent design facility. I have a last chart telling you that stakeholders ready to collaborate on this platform are several, and they expand from agencies to industry to academia. And therefore, that's the need of models, tools and standards to speak and to interoperate. Sam,
all right.
How do we interoperate?
Yes, thank you very much, Ilaria. So I'll talk a bit about that. As I said, I come from the Rhea group, or at least I work for the Rhea group, and a bit about what we do. So we're active in the space domain. That's where our heritage comes from. Nearly 30 years of providing services to the space domain, with a very strong component in both security and system engineering. It's on the system engineering part that I want to, let's say, talk a little bit with you. So before we do that, I want to give you a definition of space system engineering, which has been taken from the European Space Standards, the system engineering branch of it, which is the art to define, design, realize, and verify a system in a three-dimensional space. So across disciplines, which ties nicely into what Ilaria presented earlier, the fact that we have all those stakeholders in the concurrent design facility collaborating on one system. But also along the life cycle and through the supply chain. So you see that it poses a lot of challenges to make that happen. And even though we do more and more work with digital means, a lot of it is still done using a document-centric or document-oriented approach. And that with the increased complexity of the systems that we're, let's say, inventing and designing and realizing, documents no longer suffice, and we need to make a transition to models. Now, this is not something new. This has been ongoing for quite some time, but I did want to start with that. So we need a model to support system engineering, and in this case, very specifically concurrent design. And at the European Space Agency, this started with the integrated design model, where you have a central data repository with what I would call workspaces per domain of expertise or stakeholder that is involved in the design, databases, and also tools that these specialists use to actually do analysis. And the way that that was implemented in 1998 and later was with a large collection of Excel spreadsheets. Was a very practical approach, which allowed us to define architectures of spacecraft and let's say in all the variances that we needed, also their behavior to a certain extent, and we managed to achieve this data exchange between disciplines. So every discipline would have an Excel spreadsheet. Those spreadsheets are connected. We had the concurrent design process embedded in the tooling that we built or that was built in the spreadsheets to also manage the flow of information between the different experts. And what would come out at the end was a specification for each of the subsystems, but also for cost, risk, and programmatics on what that would mean for that system of interest. And at the end, the system engineer would be able to give you a total mass budget. The power engineer would be able to give you an energy budget on the basis of which decisions could be made and check whether the spacecraft would at least fit in the launcher envelope. So a very pragmatic approach. But we did have some challenges. It was rather informal, so not yet standardized. It was incomplete from a system engineering point of view. We were not able to capture the requirements and do verification of those requirements using the tooling. And it was also very challenging to collaborate across organizational boundaries. In essence, we had all those workbooks or those spreadsheets on a shared folder on the network, and through that, let's say, connection, we would be able to collaborate. But exchanging it with other organizations and doing then cross-organizational boundary collaboration was a large challenge. So something had to be done. But I'm showing this because I think it's important that already at that point, I think we were doing a form of model-based system engineering. And I have to say, even with this very pragmatic approach, it got the job done. And I think in excess of 100 concurrent design studies were done at ESA with this approach. And this was also the seed which was sort of passed to other organizations interested in concurrent design that started with this set of workbooks to initialize their facility and to do, in my opinion, already at that point in time, model-based system engineering. Informal, but still there was a model on the basis of which we could actually do part of what it means to do system engineering. And I think some facilities probably still use this Excel-based approach. If you then go to sort of a formal definition of model-based system engineering, and then you'll see that this word formalized is also in there. It is the formalized application of modeling to support system requirements, design, analysis, verification, and validation activities, beginning in the conceptual design phase and continuing throughout the development and later life cycle phases. So you see here that also part of the definition that I gave to you, what it means to do system engineering, or what system engineering is also captured here. So you see that MBSE is there to do system engineering, but then slightly I would say different to what was done earlier, and for sure different when it's based on documentation. There are MBZ standards in the European space domain. There is an organization called ECSS which manages, or I would say manages the standards for the European space sector. And we have two standards, one called ETM 1025. They're not yet standards, they're called technical memorandums, but at least they document what we want to achieve with them and how they should be used. So we have 1025 and 1023. Now 1025 is a technical memorandum that focuses on conceptual models in early life cycle phases, so 0, A, and B1. For those of you familiar with the space mission life cycle, that may mean something. But let's just call it feasibility work. And in phase B, you actually come up with what we call a system requirements document or model on the basis of which contracts are signed and spacecraft are in the end designed and built. What you also see in the title of the standard on the screen is that's the engineering design model data exchange for the CDF. So you see that it's very much tied to the kind of work that is being done at Concurrent Design facilities that Ilaria explained earlier. Then there's also 1023, which focuses on larger models for the later life cycle. So that's B, C, D, and E, and that captures also everything in the definition that I gave of system engineering. And also there, the title is Space System Data Repository. So a lot that is in these standards is actually about describing the language and the structure that we use to express our complex systems. Both have been developed in tandem. Where possible, a common approach has been used, and the intent is to later merge them into a real single standard. Whether 1025 and 1023 will become merged or whether they become their own thing is work that is ongoing in working groups that ESA organizes together with the large space system integrators and the national agencies and with input from industry. But you see that these standards were already devised in 2010. So we already recognized that it was important. Now, 1025 actually started from this. So we had those workbooks defined, we had concepts defined, something like an element and a unit. So the fact that you can express what it means to be a space system, like a satellite, a component on that space system, but also things we call parameters. So the mass, the length, the width, the power, consumption, and the fact that there are owners, so that you have a team of people that is coming together in a room like the CDF that own part of the system. And because they own part of the system, they have to take responsibility for making sure that their part of the whole fits the whole. So I go back to this slide. Now, I mentioned already that we have that distinction between the two standards. So one is for early phases, the one is for later phases. And the way that you organize your work is drives a lot how these technical memoranda are written and how you can use them. So typically in early phase design, you have tens of users. I think in the ESA CDF, there's place for roughly 30 or 35 engineers and scientists to collaborate to come up with the definition of what it means to be a space mission for the future. In other organizations that we work with, you have similar numbers. You have one or a couple of organizations that need to collaborate. We share the data in near real time. So if somebody changes the mass of one of the building blocks of the design, everybody sees that change almost immediately. And we use it to do trace studies. So what does it mean if we take a chemical propulsion versus an electrical propulsion, or we have that infusion of technology through the technology push that Ilaria was mentioning, so that we can actually do trade studies to see what the impact is, all in near real time using that one language. Also, what is important to realize that in these early phases, the requirements are in a state of flux. We start with a rough idea that can be 10 or 15 requirements. An example that I can give you is put 6 astronauts on the moon 10 years from now for no more than 1 billion euros. That's very high level. And by doing the exercise and finding out what it means to be that mission, you may actually end up and saying, look, 1 billion we can do, but we can only do 5 astronauts. Then you can go back to the user or the problem owner and say, do we fail? Let's say, do we say that it's unfeasible, or do you find 5 astronauts acceptable as well? And many times the responsible for that program will say, yeah, 5 astronauts will be able to do our job as well. So you see that requirements are negotiable, but you have to give proof to the requirement owner to be able to make that decision to change it, yes or no. So it supports decision making, and we have relatively small models, so they're not overly complicated. They are at that right level of abstraction to make those traits that I just mentioned. While if we go to the later phases, of course, you have many more users. Sort of imagine that we have our system requirements defined, and then a team of organizations and engineers has to then actually go into the detailed design and actually define to the nuts and bolts what that spacecraft or complex system should look like. So you have hundreds of users, tens of organizations, and the synchronization of the data doesn't happen in near real time anymore. It takes a bit more time to think about what you have to model, analyze, etc. So the synchronization is more in terms of days, weeks, and months, and for sure not in terms of seconds or minutes. And you have very formal configuration and version control. You also use strict baselining so that you go step by step and you have full traceability of what has happened along the design cycle that you're using, and you have very formal and detailed verification and validation. So you see that the way of working is rather different. And as I mentioned earlier, the transition between that more, flexible is maybe not the right word, but that more organic and fast-paced type of working happens around the first half of phase B, where we have the system requirements review in the space domain. That is where contracts can be drafted and actually industry goes off and designs and builds a spacecraft for the agency. So a bit more about 1025. So it's a technical memorandum developed by the ESA Concurrent Design Facility based on that very, very early MBSE model, which is to promote concurrent design to support collaborative model-based system engineering. And that's where I want to make a very important point. It's about collaboration and the fact that you have to be able to work with 20 or 30 people on the same model at the same time to investigate what the impact is of a change that you make and to explore ideas. And we do that in CDF environments. They can be physical, they can also be virtual. And we also want to exchange or facilitate data exchange between the different partners, not only the domains of expertise or the people that are sitting in the room, but also between customer and supplier or cross organizations. So you see those 3 aspects that I mentioned in the definition of system engineering are covered to a certain extent. Now, 1025 describes what it means to do concurrent design and gives you sort of a structure to do that, but it also gives you something called Annex A and Annex C, which are formalized statements that you can use to build software around. And the first piece of software that was built that implemented 1025 was the ESA OCDT, the Open Concurrent Design tool. But there's also industrial partners that build software around it. We have Blue Engineering, a company in Italy, which has developed COSM, the collaborative system manager, which implements 1025. And Rhea has an open source application called Comet, which is also an implementation of 1025. So you see that we have an ecosystem where it's not just ESA doing things. It's for sure not only Rhea, but we have multiple organizations building software around that standard so that we can collaborate, work together, exchange ideas, and basically come up with designs, but also specifications of those complex systems. But we do a bit more. So first of all, we have this language 1025. We have tools around it that allow us to create models collaboratively. I want to stress that. But then there's the next step. Each domain expert that contributes to the design doesn't only use OCDT or COSM or Comet to do the work with, because with those tools you can exchange data between different stakeholders, you can specify the requirements, you can make an architecture, you can specify behavior to a certain extent, but then you also need to do analysis. You have to figure out whether the architecture that you're proposing will actually meet the requirements, and you have to prove that. And typically you do that with tools. They can range from Excel to Microsoft projects, but there are of course also a lot of other tools. And what you see on the screen here is a list of all the domains of expertise that you typically need to come up with a space mission design, and also the tools that they typically use. Currently, Rhea is involved in a project for the European Space Agency to create what we call an engineering hub or a digital engineering hub around 1025, where we make connectors to those other tools that are frequently used in industry, or let's say by the engineers to do their work, to make sure that we can transfer data from one tool to the next, so that you can use, for instance, ESATAN TMS to do thermal modeling, EcoSim Pro to do simulations together with MATLAB. There's also CATIA to do the 3D configuration, so that you can benefit from all those tools and basically use 1025 as a glue between them to make a complete enough description of what it means to be the problem, so the requirements, and the solution, proving that it can work. Then I also want to mention that there's Astos from Astos Solutions, an application to do, let's say, orbital mechanics. And then we also have other architecting or system engineering tools that are very popular in industry, not only in space, which is Capella and different SysML tools, which are also system engineering tools. So you want to be able to benefit from all of those tools. They are complementary to each other. They are very strong in some points, not so strong in others. And you need this whole set of tools to come up with your design. So those are being developed by Rhea. I have to think, there's Astos Solutions doing Astos. We have OHB helping us to specify. So OHB is a large space system integrator in the European space industry. They help us define what their requirements would be so that their users in their CDF can actually work with it. And then we build the integrations. But Rhea and the companies involved in the Engineering Hub activity are not the only ones. There is work ongoing to include augmented and virtual reality. There is work ongoing to develop tooling to compute or analyze, let's say, debris that might be left in space and how to deal with that. So the debris mitigation facility is being tied to 1025, so that if you design a spacecraft, and Ilaria showed that we also have to sort of worry about what happens when the spacecraft is done its job and it's at the end of its life. We have to do something with it. We can't leave it just in space and be trash. We have to either deorbit it or do something with it, so that you can do, let's say, part of the analysis is done with the debris mitigation facility, which will be linked to 1025. And we also do life cycle analysis. Also, those tools are tied. So you see that an ecosystem is evolving around 1025 to do early phase design, early phase collaborative model-based system engineering, and the ecosystem is growing, which is, I think, is fantastic. Of course, the journey is not finished. And the message that I want to leave you with is that it's an ongoing journey. I think the journey is more important than the end result. And in the European space sector, we keep each other up to date on where we're going, what our experiences are. And every year, the conference is organized. So MBSE conference, we have the MBSE 2021 this year at the end of September, where we exchange practical experience, lessons learned, novel ways forward, software tools for both space system and software architecting. So if you're interested, it would be good to potentially follow that, sort of to show that this is an ongoing journey and we're far from reaching the end. But I think the journey is more important than reaching the end, and things keep evolving all the time. So with that, I finished what I had prepared, and I'm hoping we have questions from the audience. So I would say give the audience an opportunity to maybe enter into a conversation with us, with Ilaria and myself. So if you have any questions, feel free. See if the chat is open. I'll open the chat again. I heard a pling that I don't hear.
I'm trying to understand.
You see the question?
To be honest, no.
No, I don't see anything either.
Yeah.
Doesn't sound like anything will be coming.
And, yeah, in the meantime, if there's nothing coming up. Actually, I wanted to maybe propose some to spend a few words also to the non-space applications that we are having with concurrent design and with the modeling and tools for that.
Yes, absolutely. Yeah, that's a good point. Let's say I learned the trade of concurrent design in the European Space Agency. I worked in the same section that Ilaria is now the section head of. At one point, we were colleagues there. So I learned the trade there, and I learned about 1025 and all the tooling around it. And currently, we also apply concurrent design in a similar fashion to other industries next to space, where we also use 1025 and COMET to support the exchange of data. And I think that's important to mention that 1025, even though it was created at European Space Agency with, let's say, partners in the space industry, it's a general purpose collaborative models-based system engineering language and set of tools. The team that I work with has applied this in luxury yacht building. So it's not only in space, but also for luxury yachts. There's a company in the Netherlands that has been so successful with concurrent design, and they find it so important that they've built 3 dedicated facilities, which are also connected together so that they can work together on common problems. It's also being used at the Dutch Ministry of Defense, where we've done, I think, in excess of 20 concurrent design studies. And their situation is very similar to ESA. The organization that we're working for is the Dutch Materiel Organization. They don't design anything themselves. For sure, they don't build anything themselves, but they need to be a smart buyer. So their responsibility is to think what they need for the future, to come up with specification for that, and then ask the market to either build something new or deliver that. But they need to be a smart customer. So they go through concurrent design, they use the tooling to actually come up with a potential solution, understand what it would take to do that. Again, technology push and pull is important here. How long it would take to get such a system, and to also get a handle on how much it would cost them, so that when they go out to tender and they have the requirements that they ask their suppliers to respond to, they have an idea of what the system could cost, what the risks involved are, and for sure they've involved their own users to help specify the problem in a correct way. And it's being used for systems like frigates, so large maritime Navy ships, all the way down to the oil distribution centers that are the responsibility of NATO, where the member states each take a part in making sure that kerosene gets to where it needs to be in case of a calamity, which could be a natural disaster. And of course, worst case scenario would be a military conflict. So they pump around oil and kerosene all over Europe. And one of the questions was, how do we make one of the stations future-proof? What does that mean? And it means you need an oil pump, you need electricity, and you quickly see that even though it's not as complicated as a spacecraft or as a frigate, it is complicated enough to sit together in a room, have those stakeholders involved, understand the problem, understand the potential solution, and characterize it using 1025 and do analysis to determine how much will it cost, how much power does it need, what could be the layout in a building for all the systems, etc. So yeah, equally applicable to non-space domain. Lots of domains in which you have very complex systems where collaborative model-based system engineering and concurrent design are of a huge benefit.
And I hope that this triggered some questions or some ideas, inspiration in the audience. So don't be shy also to throw some ideas for discussion that we can, let's say, have a chat together about. And building on what Sam just mentioned, because we are very much going to address products, technologies, but I'd like to mention also the versatility concurrent engineering as an approach, as a methodology to produce something different than a product. And so, for example, we use it for route mapping. So putting together ideas and, for example, prioritizing them or based on some criteria that you might want to discuss in a plenary environment where different expertise or actors are on the table. We have one question, I understood. Is that correct?
Yes, there is one question, but I don't see it. So it would be good if the moderator can help us.
Yeah, we cannot read it.
No, we can't see it. So maybe if the moderator of this webinar can read the question out loud, that would be good.
Otherwise, we will not have a way to answer.
Yeah. And maybe, Ilaria, it would also be maybe interesting to sort of see where you see the future of collaborative model-based system engineering in the context of concurrent design. So we're working on those tools together with you, basically, with your section and the agency. What do you see as sort of things that might happen in the future?
Yeah, we are very much working, in fact, together with Rhea, with the companies that Sam has mentioned, and to work on this interoperability, semantic interoperability first, but of course, collaboration interoperability as such. We want to bring together all the disciplines, so to connect the disciplines, the project life cycle, and all the supply chain. So basically, we want to connect all those actors taking place and taking part to the end-to-end space mission development from the design phase to the implementation, meaning the procurement of hardware, assembly, integration and testing, verification, and closing the loop with the verification and validation of requirements up to launch and operation. This means, of course, in practical terms, that we have to connect our models and that we have to understand how to exchange data. We are discussing a lot about model-based systems engineering because this is the, let's say, our space step for digitalizing the engineering. In ESA, in the European Space Agency, the process of digitalization is broader than that, but as being part of the technical directorates, myself and the CDF, we are taking part, active part on this MBSE development. So having tools and having standards to exchange data via these tools is the essential, let's say, aspect we are looking at. And moreover, we find instrumental for that discussions with all the stakeholders. So we have fora for debating about what is needed, what are the priorities, what do we have to enable. We have an advisory group called NB4Z involving industry, for now the LSI, national agencies and ESA, so all the major actors to shape the future in this direction, to discuss how to apply and what do we need to develop. And out of that, of course, we identify the technology developments which are required. These in practical matters translated to the invitation to tenders which are open not only to space actors, and I would say that in fusion with non-space, so this touch base of space and non-space is now essential, and we can exchange methodologies and tools and also ideas to strengthen and to try to be together in this challenge, which is not small at all.
Yeah, no, absolutely. So thank you, Ilaria. So very interesting, and you see that there's a long journey ahead of us that we've embarked on some time ago, and it keeps on going. And there's so much exciting things going around. We also have infusion of artificial intelligence to see how we can benefit from getting, let's say, computers to help make better and faster decisions potentially, and then also the other technologies that I sort of explained that are being brought into the 1025 ecosystem. And then, of course, there's always the challenge to build tools that users can use. It's one thing to have a tool or basically come up with a language in a tool with which you can express it. But then there's always the challenge to build it in such a way, which is really, really difficult, that people from different areas of expertise can actually read the models, work with them, interpret them, because they are different in nature than a report. So I find it understandable why we've done document-centric work for such a long time, because basically you can read things like a story and make sense of it. And with models, that is a big challenge to make a story around them so that you know how to navigate them and to interpret them and work with them and collaborate on them. So building one together, I think we have a handle on, but then giving it to somebody else so that they can interpret it and understand it is yet another challenge. So a lot of work to be done. I find it super exciting. I'm really happy to be a part of that community. Yeah, and I think with that, I have nothing more to add. Ilaria, if you want to make a closing statement.
Yeah, that is just, yeah, this is just the conclusion of the beginning of the start. And yeah, I want to thank the audience for listening to our words, and I hope that we have inspired some thoughts. And even if there are no questions in the chat nowadays, you have our let's say names and contacts in the page of the event, so we are happy to exchange ideas and thoughts with you.
Yeah, so I go back a couple of slides so that there's, let's say, the last one is also the one from Isa, so that you see where you can find the Concurrent Design facility on the ESA website. I would advise to go there, check it out, and get in touch with Ilaria if you need more information on what ESA is doing. And with that, we leave you. Thank you very much for listening, and enjoy the rest of the conference. Bye.
Bye-bye.